In this video, I'm going to talk about bonding between elements in a compound. And there are basically three types of bonding, and they're often described as ionic, which is a transfer of electrons from one element to another, covalent, which is a sharing of electrons between two elements, and metallic, which is a sharing of electrons in a different way between metal atoms. So these are our three types, and I'm really going to be focusing on the top two, ionic and covalent. For metallic, basically you have metal atoms in a crystal situation, packed in if it's in its solid form, and the outer electrons are held very loosely, and so this electron can move around this atom, it can move over to this atom and move over to this atom, and it can just keep moving around all through, and they're all doing this. So there's sort of like this sea of electrons, and so those electrons are called delocalized because they're not confined to one atom. They can move all throughout. But we're going to focus mostly on ionic and covalent for the rest of this video. So when first learning about bonding, we often think that it's one type of bond or the other type of bond, when in reality there's this continuum where you have covalent bonding on one end and you have ionic bonding on the far other end, and it's this continuum between the two, and a bond might be here or right smack dab in the middle, which would be 50% ionic and 50% covalent, or it might be over toward the ionic end. So bonds can be sliding along this continuum, and if it's lower than this 50-50, then we consider it to be a covalent bond, but the closer it is to the ionic, the more ionic type properties that bond will have. And the same with ionic. If you're in the far end, it's very ionic and has ionic properties, but as you slide it toward the covalent, it gains covalent properties and lessens the ionic properties. You have to sort of think of it as this continuum that can slide back and forth depending on what the elements are that the electrons are between. So bonding always has to do with at least one pair of electrons between our atoms. So as the atoms come close to each other, here's the nuclei, which has a positive charge, some number of positives depending on the number of protons. And in the middle here is where these outside shells can overlap. And each of these atoms puts an electron into this shared space. We're going to have one electron coming from this atom and one coming from this atom. So let's say these are atoms of the same element. Let's say this is hydrogen and hydrogen. We have an electron from one hydrogen, and we have an electron from our other hydrogen. Now, these two hydrogens, since they're the same element, they have equal strengths pulling on these electrons. So the attraction that these electrons have for the right nucleus is the same as the attraction they have for the left nucleus. So these two electrons are going to be right in the middle between the two nuclei. And this would be a perfect 100% covalent sharing bond. And you only see that when it's elements of the same atoms of the same element that are bonding together. When the atoms are different elements, it comes down to this property called electronegativity. And electronegativity is how strongly an atom will pull on the electrons of the next door atom. So it's pulling on somebody else's electrons. And if we look at this, we'll see that over here, 0.07 has a very low electronegativity. And as we move across 1.8, 2.2, we notice that it starts to increase until we get to fluorine, which is an electronegativity of 4. This is our highest on the whole periodic table. So fluorine is a big bully. It pulls electrons very strongly off of other atoms or closer to itself. Now hydrogen over here is 2.1, and you notice that it's pretty high compared to the rest of its column or the column next to it. And so hydrogen really belongs kind of over here, because this one's 1.5 and this one's 2.5. So hydrogen really belongs sort of around that location there when we think about this. This is our low end of electronegativity down here on the francium end. And this is our high corner over here where fluorine is. You have to think about placement when you think about bonding. Placement on the periodic table. So let's say we're looking at a bond between calcium with an electronegativity of 1 and bromine with an electronegativity of 2.8. So calcium is 1, bromine is 2.8. That means bromine is almost 3 times as strong pulling on the electrons as the calcium is. Notice they're very far apart on the periodic table. We have a metal with a non-metal, and traditionally we would call this an ionic bond because the bromine is so much stronger, it kind of steals the electron from the calcium. So if we look at our picture again, if we have calcium on this side and bromine on this side, what happens is, here's our nuclei with their positive charges, and calcium's putting an electron into this bond and bromine's putting an electron into this bond. Let's change this a little bit just to make it more obvious. Now, if this was a perfect covalent bond like the last one, our electrons would be right here in the middle. But we said bromine was much stronger. It's a 2.8 electronegativity, whereas our calcium was only a 1.0. So this one is pulling, there's almost 3 times the attraction for this nucleus on this side. So the electrons aren't going to be in the middle. They're going to be way closer to our bromine side. And when they get pulled that far over, you consider that bromine has the electron and calcium has lost the electron. And it's actually been transferred to the bromine. So this would be an ionic bond if they get pulled way over toward one side. And they're always going to be pulled toward our fluorine. So whatever's closest to fluorine is going to have a higher electronegativity than anything over here, and so the electrons will be pulled closer to the fluorine. So that's why a bond between a metal and a non-metal is considered to be an ionic bond, because the electrons are pulled further toward the non-metal, and they're pulled so far over that we consider that the non-metal has actually taken them away from the metal. Notice that helium and the rest of this noble gas column, they all say not applicable because they have a full outer shell and they don't want any more electrons, so they're not pulling on electrons from other atoms, so they don't form bonds. So when we're looking at our high and low electronegativities, we have to sort of pretend like our noble gases aren't there because they're not going to be involved with bonding. So as a general rule, if you have an ionic bond, it's going to be between a metal bonded to a non-metal. They're far apart on the periodic table. Covalent bonds are nonmetals with nonmetals. And remember, our nonmetals are over here in this little triangle. So it's going to be like between carbon and oxygen, or hydrogen and oxygen, or phosphorus and bromine. They're both going to be here in the periodic table close to each other. And of course, our metallic that we talked about at the beginning is a metal with another metal. And that's where we have our sea of electrons. And remember, the metals are on the left and the middle of the periodic table. And both elements will be in that area. So that might be something like calcium and chromium, or strontium and nickel, or copper and zinc. So let's look at some properties that you get from these different types of bonds. And remember, the closer you are to the covalent end, then the more covalent properties they'll have. And the closer you are to the ionic end, the more ionic properties you'll have. So ionic properties, they form crystals, which means they are bonded in a crystalline shape. There are 7 different crystalline shapes that they can form. They are hard and brittle. Think of table salt and ACl. To crush those crystals would take some force to break those ionic bonds. When you melt it to turn it into a liquid, or boil it to turn it into a gas, that's a very high temperature to do that, because for an ionic compound, in order to separate these ions and allow them to flow like in a liquid, you have to actually break the bonds between them. So it takes a lot of heat to do that. If they're in their solid form, this crystalline form, they're all locked in place. So it won't conduct electricity, which is the movement of charged particles, because they can't move. They're stuck where they are. But if you melt this and they're free to move apart or move around, then they will conduct electricity. Often, our ionic compounds are soluble in water because water's polar and it can gang up on these ions and surround them and pull them off of the crystal. And so this will come apart when you put it into water. If you try to put it into something that's non-polar, then usually they will not mix. So if you try to put table salt into vegetable oil, it will just sink to the bottom and nothing will happen. But if you put it in water, it will dissolve. High enthalpies of fusion and vaporization. Enthalpies of fusion is the amount of energy it takes to melt, and vaporization is the amount of energy it takes to boil a gram of the substance. And again, we said they had high melting and boiling points, so those are going to be high numbers. And because in their solid form they're locked in place and they can't move and they don't conduct electricity, they make really good insulators, because electric insulators keep the charged particles from moving, and when they're locked in place, that's what happens. So that's some of the properties of an ionic compound. If we compare that to a covalent compound, remember our ionic compounds are crystals and in their solid form. But covalent compounds tend to be liquids or gases. Sometimes they're solids, like table sugar is a covalent compound, and it's a solid at room temperature. So it can be in any of these different forms, but if it's a liquid or gas, it's probably a covalent compound. So at room temperature, think about water. Water is a liquid at room temperature, and that is a covalent compound. Melting points, we said ionic was high, covalent's low. They do not conduct electricity, even as a liquid, whereas, remember our ionic compounds, if you can melt them, then their particles are free to move, and their particles are ions, charged particles. But a liquid form of a covalent compound, when you melt water, for example, if it's ice and you melt it into water, it's still H2O. We haven't broken any bonds. We've just separated the molecules from each other a little bit and freed them up to move. It will not conduct electricity. Solubility in water. Water is polar. So ionic compounds, which are charges, and polar, which are charged ends, they mix really well. But often covalent compounds will not mix as well. And usually covalent compounds do not conduct electricity because, again, we're not pulling the atoms apart. When we melt it, it's still the same molecule as it was before. I hope this has helped. Please watch other videos and like and subscribe. Have a great day.